All right. You guys are gonna have to help me out a little bit because I had people in my office up until class, and I would try to check what we went through. I know we kind of covered confidence intervals last Wednesday. Just kind of reminding, did we talk about things that change the width of the confidence interval? Okay, I think I'll start there because I think that I kind of held off on that. If not, it'll be good for us to review. But we did work through some examples where we calculate these confidence intervals, so upper and lower bounds. And let me get this open. So as I'm opening this, so we went through a couple examples where we calculated upper and lower bounds and created these confidence intervals. We're looking at kind of examples where we didn't know what the true population mean was. And the best guess that we had was whatever our sample mean was that we calculated from our sample, because that's all we could observe, right? So we had this equation that looks something like this. So we took our sample mean. We then added what we were going to be calling our margin of error. That was kind of the term we're using for it. And that margin of error was calculated by finding the z-score that gave us alpha over 2 on each side of the confidence interval. So remember, alpha was like if we wanted the 90% confidence interval, what was the alpha there? So we said the interpretation of alpha was the percent outside the confidence interval in decimal form. So 5% would be outside, or sorry, 95% confidence level. 5% would be outside of it. In decimal form would be 0.05. We then knew that there was half of that on each side, so 0.05 over 2. So we now know that the area that we would have in the tail, there's some z-score that corresponds to having 0.025 in each tail. So we would kind of use that it's the same value, but the negative value gives us our lower bound. The positive value gives us our, this is a z, by the way, sorry. The positive value gives us our upper bound, right? And this represents the number of standard deviations away we need to go. So the number of standard deviations away that we need to go multiplied by whatever our standard deviation is for that sample mean, right? Which we know is just the square root of the population variance of the data we sampled from divided by our sample size. So we started out, this seems a little impractical. You know, how do we know the population but not what the population mean? Sorry, how do we not know the population mean, but we know what the population variance is? Well, it's not the most realistic, but it's where we have to start, right? So I don't think we'll get there today, but Wednesday we'll talk about the more realistic scenario where we only have a sample variance. But we'll start out here to kind of get a base knowledge, right? So we've got a couple different components in this margin of error, right? If we see a different sample mean, that's not going to change the width of our confidence interval. It's just going to shift where that confidence interval is, right? So the first thing we can think about is, what if I have a larger alpha value, right? I've really got three things that could change here: the population variance, sample size, or whatever alpha I want. Right? So when I'm thinking about a larger alpha, what I'm really saying is, if I was to go from a 95 to a 90% confidence interval, my alpha would be going from 0.05 to 0.10. Right? So a larger alpha, saying things with a lower level of confidence, means that we're going to have a greater area in that tail or a greater value for alpha. Right? So if instead of going from a 95% level, I want to say something with 90% confidence, instead of 0.025 in each tail, there would be alpha divided by 2, so 0.1 over 2. There would actually be 0.05 in each tail, which would correspond to a z value that's a little bit smaller. Right? When I say smaller, I say that because I don't want to say less than or greater than, because it depends if I'm looking at the positive or the negative value, but it results in a z value closer to 0. I want to go out fewer standard deviations away from the mean. So when I have a larger alpha, it means I have a larger area in the tail. How do I get that? Well, I have to choose a smaller z-score. So if the z-score is smaller, what's going to happen to my margin of error? If this value goes down, what happens to the margin of error? It also goes down, right? If I haven't changed anything else. So if I have the same standard deviation, but instead of 2 standard deviations away, I'm only going 1 standard deviation, what's a smaller value, right? So I'm going out not as far from that sample mean. So I'm going to end up with kind of this smaller or kind of narrower confidence interval, or narrower range of values. So lower level of confidence corresponds to a higher alpha value, which means I would need to choose a smaller number of standard deviations or a smaller z value there. So that would decrease my margin of error, which then decreases the size of my confidence. What if I chose a larger sample size? Right? So let's say, kind of try to use different colors here. So now I want to keep my level of confidence the same, right? But I take a sample and find the same sample mean, but using a greater sample size, right? So if I have a greater sample size here, what's going to happen to my margin of error? Remember, this whole thing reflects my margin of error. Yeah, if I divide this by a larger value, the standard deviation of my sample means gets smaller, right? So this guy gets kind of smaller. That's what this represents. I haven't changed the level of confidence. I've just changed my sample size. So my margin of error is smaller. I'm adding and subtracting a smaller value to that sample mean. So a larger sample size also results in a kind of smaller, narrower confidence interval, which is actually a good thing, right? Because I'm now able, with the same level of confidence, to be able to say, well, with 99% certainty, now I can tell you the true population mean is not just in between 10 and 20, it's in between, I don't know, 14 and 16, right? I get a much narrower range of values, which if I'm making projections or decisions for the future, that's a really good thing, right? I want it to be able to narrow down where the true population mean is as much as I possibly can. So taking a higher sample, we kind of talked about when we were talking about distribution of sample means, if that higher sample decreases my standard deviation of my sample means, I'm getting a much more peaked distribution. Having a much more peaked distribution meant that kind of values near the mean were much more likely for me to see if I was only getting 1 sample. So these are 2 things that we can influence. We can say things with different levels of confidence and change the size of our interval. We can take smaller or larger samples, which will alter the size of our confidence interval. And then the last thing would be, well, what if the population variance was higher, right? So now if the population variance is higher, what's that going to do to my margin of error? Make it larger. I'm adding and subtracting a larger value to my sample mean, so my confidence interval will actually here get wider. Now, this one, I shouldn't say it's not as interesting, but it's not as interesting because I can't change what the population variance is of whatever variable I'm sampling from, right? That just is what it is, right? But we know that if we're sampling from a population that has a larger variance, so maybe like I'm comparing countries and looking at income. Well, if one of those countries has a much higher variance in their population variance in their income, automatically I know that when I build my confidence intervals, they're going to be much wider. So that's kind of why that we would still want to know that and why that might be useful. But in practice, right, the things we can change are really just 1 and 2 here. Okay? So we then worked through, we had the hockey puck example, we had, I think we did a weight one, I did the weight plate example, so I was able to kind of go back and see where we left off, and this was the example that we kind of ended on, right? So we built these confidence intervals. This one we said, we could tell the company you're not hitting your target goal, right? And that's where we kind of ended, right? So we'll leave this up here, right? Oops. So we've got our different confidence levels and the alphas that correspond with that. So today, we're basically going to be taking this and seeing how we do it in Excel, okay? So I'll start out with that, then we'll progress to the next topic, and we'll come back and do a little bit more work in Excel, right? So there should be a file under Files tab, go to in-class data. So this confidence interval is blank. We're going to kind of work on today, and we're going to build one of the worksheets, or at least I'll show you how we could build the worksheet. I'll eventually post the complete version of this once we work through it in class. But for now, it is blank. So let me zoom in so we can see this here. So I've got a couple kind of things going on here. One of them I'm going to change later, but for now, we'll kind of look at this data set. We've got a bunch of different universities. They're male, female, and total undergraduate enrollment. So if you can kind of see the titles, I kind of minimize them just so that we don't take us up as much space. So what I'm going to do is try to build a confidence interval based off this sample for what the true population mean enrollment size is for universities. So I don't have every university here. I've got like 100 of them. So we're going to build a confidence interval based off this sample. Now, this is where it gets a little goofy because I said we have to walk before we can run. So we have to understand how we work with a population variance before we only have a sample variance. So here, assume that someone told you, you don't have the population data, but someone told you the population variance is whatever I have in this cell, right? 68, is that 68 million, right? So I have a known population variance, right? And actually, I'll just label this just so we make sure we know that this is like something we were given, this population variance. Ignore the cutoff for right now. That's something else that if we have time today, I'll kind of show you. We've really already looked at examples of what I was going to use this for. We use a different data set when we were looking at how we do, what's the probability we're above or below a certain cutoff. We did that with like the Indiana weather data. So we can kind of ignore that for now. So I'll actually just to kind of move this down here and move my sample size up here because we don't need this for right now. So if I'm looking at that total undergraduate enrollment, I can find my sample mean by simply finding the mean in Excel, which is the average function, right? So equals average. I'll select that very first observation, hold Control Shift or Command Shift on a Mac, hit the down arrow. It selects all of my observations for me. I then hit Enter, sends me back up, and I've got my sample mean here, right? So once again, if it kind of helps to label these a little bit more specific, that's my sample mean that I'm calculating. Because I only have sample data here. I don't have every university. To get my sample size, we said we can count the number of observations we have by using the count function, right? So I'll select that variable in my count function, hit Enter. Got 111 universities here, okay? So it's a pretty good, pretty high sample size. Now down here, I'm going to start to show you how do we create our confidence intervals based off this sample mean. A lot of it's just going to have Excel do some math for us. Now, I think it's probably easier to set it up in this first way I'm going to show you. So down here, one of the components that we needed in this confidence interval equation was the standard deviation of my sample means. If I wanted to, I could enter all this into one cell in Excel if I wanted, but I'm going to break it down just I think it makes it a little bit more clear. So down here, I'm going to find the standard deviation of my sample means. Oh, I did not want to do that. Hold on. There we go. So equal sign, I need to take the square root of my population variance divided by my sample size. So I come up here, take my population variance that was given to me, and I'm going to then divide that by my sample size. Okay. So that should give me this standard deviation of my sample means here. Okay. The next thing that I need, I've got that part done, I need my sample mean. Well, I have that up already in a cell. The only other thing I need is that z-score that gives me the desired alpha over 2 in each side of my confidence interval. Okay. So we already actually have looked at the function that we can use to find that z-score. In practice, we went to the table, found the value in the middle, right, that probability that was as close to alpha over 2 as we could, and then went over and up to the row and column heading and found that corresponding z-score. In Excel, that process, right, we're looking up the probability to then find the z-score that corresponds to that. We're working in reverse, or we're looking at the inverse kind of transformation. So we said we can use the norm.s.inv function in Excel to do that for us, right? We don't have to physically use the table. Excel will like kind of look it up in the table for us. So what do I have to tell this function? Well, I just have to tell it the area I want in that lower left tail. Okay. So I want alpha divided by 2. All right. Now the problem is going to be if I look up, Let me erase this so we have a visual here. Where's my eraser at? So if I have I want to look at the z-score that gives me alpha over 2 in that lower left tail, and then the positive one would give me alpha over 2 in the upper right tail. So I can tell that function alpha over 2, but it's always going to tell me that negative z-score, right, or the negative z value. But remember, that's already built in when we calculate the upper and lower bound. Right? So I kind of want to ignore that negative sign, right? So if I hit enter here, it gives me negative 1.644. If we did this by hand, we would have found that we were in between negative 1.64 and negative 1.65. Here we can be a little more precise with Excel. Yeah. Yeah, so the purpose of the Excel assignments, right, is you should be using all the built-in functions and formulas in Excel to do that assignment, right? So if you just type in 1.6, well, good on you if you do the integration and find it out to like the 4th or 5th decimal point. But if you just put in 1.64 here or 1.65, you're not going to get full credit for that, right? Because the purpose of these Excel assignments is to be using the built-in functions and formulas in Excel, okay? So these is like problems, what, 2 and 3, I believe, are the ones we haven't covered on that Excel assignment. So we'll go over both of those today. And then we had that due date changed on that. I can show that to you here right now. All right, so that's the end of the week, right? End of the day on Friday, okay? Gives you time to kind of work through this. If you have any questions, come to office hours or email me, right? But we'll work through kind of those today. Any other questions before I keep moving here? So it's negative. I don't want it to be. I just want the z value, or I just want the absolute value, right? So if I use this absolute value formula in Excel, ABS, it just, oh, come on. It just drops that negative sign, right? So now I should get the same value, but notice positive, okay? Now, I'm going to build 3 confidence levels here. I'm going to insert a column. So I just right-clicked and inserted a column here. Because I just want to have, be able to connect this at the alpha of 0.1, what level of confidence does that correspond to? 90, and then 95, and then 99. Right? So I'm going to build 3 different confidence levels, and I can do it relatively quickly. Right? The only thing that's changing when I'm building a confidence interval for a different confidence level, right, different level of confidence, is that z value that I need. Okay? So if I copy this down, it's going to update to my new alpha, so I can get the z values I need for those 3 different levels of confidence pretty quickly. There's no need to type it in again, right? If I've constructed it this way. So the next thing I'm going to do, I have all the components now that I need to find my upper and lower bound. Okay? So for my lower bound, at this point, it's really just using Excel to be your calculator. Right? So the main advantage in Excel here when I'm doing confidence intervals is to use that norm.s to ind function. Okay? Now, if you try to do this and you Google how to do confidence intervals in Excel, there are some other functions that we're not going to cover. The reason I don't cover them is because they are somewhat limited in their use once we get to future topics. So you can try to use them. Occasionally people will do it. And if you use it correctly, I'll give you full credit. But I would say 95% of people that try to use the other form that you might find if you Google this don't do it correctly and don't get points because they get answers that are wildly incorrect. Right? I'm showing you this way. It's probably the most universal to all of the types of problems we'll kind of see here for the next couple of weeks. So try to set it up the way that I'm showing you it this way for a reason. This is the easiest way to do it. And this is the way that it'll probably kind of fail safe to not make as many mistakes. Okay? But at this point, it's really just using Excel to be my calculator because all I'm going to do is take my sample mean. I'm then going to subtract my margin of error to get my lower bound. So I'm going to subtract that z value or the number of standard deviations the way I want to go, and then multiply that by the standard deviation of my sample means. It's as easy as that. I'm just using Excel to be my calculator. clicking on the values. Notice I don't have to round to 2 decimals, right? So I hit enter. I've got my lower bound for the 90% confidence level. If I wanted my upper bound, instead of typing this in again, I think probably an easier shortcut to save a little bit of time. I think I've showed you this before, but if I double click on the cell so it shows me the formula, I can copy that. I'll hit enter to get out of the cell, double click where I want the upper bound, and paste it. When I copy paste this way and I don't just drag across cells to copy, none of the cell references change. I should get exactly the same value. Okay? But the upper bound, it's going to be the exact same equation, except instead of subtracting that margin of error, I'm going to add it. So now I've got my upper and my lower bound. So with 90% confidence, I can say the true population mean enrollment in D1 universities is somewhere between 19,100 and 16,500, or whatever the exact numbers are. Now, if I try to copy these down, I'm going to run into a problem. Well, that definitely does not look right? So the issue is, all my cell references started to change. And when I'm doing different levels of confidence, the only thing that's really changing is that Z value that I'm using, okay? So I'll go back up here. I'll say, oh yeah, the only thing I want to update when I copy this down is that Z value. So I'm going to freeze everything else. So F4 or Command T on a Mac, I'll freeze those. I have to do the same for my upper bound. The only thing I want to change is that Z value. So freeze everything that isn't a cell reference for that Z value. Okay. Now when I copy these down, it keeps that standard deviation of my sample mean the same, and it keeps the sample mean the same. The only thing that's updated is that Z value that I was selecting. Okay. So I've now got 3 confidence levels relatively quickly. I think a lot quicker than I could do by looking up, trying to find these Z values by hand. And also I can be a lot more precise. I don't have to round anything to the second decimal here. Okay. Any questions over anything that I did here? Want to see a cell again, or? Okay, so point out a couple things. I said earlier, when we want to look at a larger alpha value, right? So if we're going from like 0.01 up to 0.1, that should mean I have a larger area in my tail. My Z value should be getting smaller or closer to 0. Sure enough, as I'm going to larger alphas, my Z values are getting smaller. We also said that if I'm going from a smaller to a larger alpha, the fact that the Z value is smaller, my margin of error is smaller, and my confidence interval gets more narrow. So my lower and upper bound should be getting closer to each other, right? So notice my lower bound is getting higher, my upper bound is getting lower, or those two things are getting, I'm getting a much narrower kind of range of values. Okay. Another thing that we could have done, instead of using this absolute value function, oops, there we go. Notice I know that I want alpha over 2 in this tail, in the lower left tail and the upper right tail. Well, if I want alpha over 2 right here, the area to the left of that would be what? Just 1 minus alpha over 2. If I just want the total area to the left, right, I know I want 1 minus alpha over 2. So if I tell that norm.s to I and v function 1 minus alpha over 2, it should give me that Z value, but positive, and I shouldn't have to use the absolute value function. So let's try that out, see if I'm just full of it. All right, so 1 minus alpha over 2. Sure enough, it should, if I copy this down, give me the exact same values as if I use the absolute value kind of way of doing this, right? And just telling that norm.s.I and v, just telling it alpha over 2. And so kind of 2 different ways of finding that Z score to just get the value to be positive, okay? Any questions on that? Okay with that? All right, so there was one more thing I wanted to show you here, and now I don't remember what it was. Oh, I know what it was. So since we already talked about things that change the size of the interval, let's assume for a second that, and this is hypothetical, but let's assume I found the exact same sample mean, but instead of from this sample of 111 schools, let's say I had another sample of 300 schools. Okay. So if I had found the same sample mean, but it was from a sample of 300, what's that going to do to my intervals, right? Well, my sample size is larger. It's going to drive down that standard deviation of my sample mean. So when I hit enter here, everything will, right? I had cell references, so everything will update. So my standard deviation of my sample mean should get smaller from a larger sample size. My margin of error would then get smaller, and I should get narrower intervals. So changing this from the actual sample to a hypothetical sample of 300, this should get smaller, and my intervals should also get smaller. Sure enough, went from what, 700 to 400 something, and these are kind of much narrower intervals, right? What were they before? So instead of 17 to 1860 or 18600, they were 16,000 to 19,000, right? So changing that sample size to 300 narrowed my confidence intervals because it was decreasing that standard deviation of my sample means. Okay. Any questions over that? Now, that was kind of purely a hypothetical kind of practice, right? Our sample size is what it is. But that kind of shows you that having a larger sample is always more beneficial when we're trying to build these confidence intervals. Okay. So if there's no more questions on that, we're going to kind of move to, well, we talked about the distribution of sample means, and we talked about the distribution of sample proportions. There was a reason why. It was to set us up so we could build confidence intervals for where the true population mean was using our sample mean, and to build confidence intervals for where the true population proportion is based off of just a sample proportion. So what we said about the distribution of sample proportions was that it should be centered around whatever that true population proportion was, and the standard deviation should be whatever that true population proportion was times 1 minus that divided by our sample size. Now the issue is when I'm building confidence intervals, if I try to do the same thing I did for sample means, right? I'll base it now off of my sample proportion instead of my sample mean. I'm looking at a slightly different statistic. I can still use that standard normal distribution to give me alpha over 2 on either side of my confidence interval. Well, this tells me the number of standard deviations the way I want to go, but I don't multiply by the standard deviation of my sample mean. I now multiply by the standard deviation of my sample proportions. Now I have an equation for this. So I could do it all at one time, all in one formula here. And this is going to be the equation of my confidence interval for a sample, for using a sample proportion to build a confidence interval for the true population proportions. Now the one problem here is if I'm building a confidence interval where the true population proportion is, how am I using that in my formula? Well, I'm not. When it comes to proportions, we're going to use the best estimate for what that population proportion is, which is our sample proportion. So we'll have to kind of estimate that using our sample proportion. But as long as we have a sample size over 30, it should be a relatively close approximation. Well, now, I mean, we're usually told, or we can find what our sample proportion is. We know what our sample size is. We know how to look at these z-scores. Once we plug all those values, it's a matter of getting this underneath a calculator, or a lot more simple equation. Now, one thing that we'll work through a couple of examples, we may not be directly told, oh, the sample, like, we were dealing with that maternal smoking variable a couple classes ago, where like the proportion of women who smoke was like 0.18, right? But what that's really doing, the way that we're coming up with that in practice is we have this huge data set. We count the number of women who were smoking while pregnant, or kind of similar to things we've done in the past, the number of successes. Now, I don't think women smoking while pregnant is a success, but success is right, whatever we're looking for, you know, the probability of the proportion of. Right? So we want to find a proportion of women who smoke while pregnant. We count the number of women who smoke while pregnant and divide it by the total number of observations, which that's really just our sample size. We'll see how this plays out in an example here in just a second, but sometimes we have a little bit extra work to do, which is calculate what that sample proportion is. Just like in these problems I'm giving you, I'm telling you what the sample mean is, but in practice, right, we know how to find the mean from a data set. Right? So we actually have to find the sample mean ourselves, just like we did using that Excel data. So don't worry too much about this. I'll never give you an example where this is the case, but if our probabilities are relatively small or relatively high, we need to make sure our sample size is high enough to kind of pass this threshold of 5, but as long as we have the samples that we're dealing with that are usually relatively large, this never is an issue. Right? But if we start to get really small samples, we have to double check to make sure that those two equations hold. But I'll never kind of throw that in there. We'll be on a problem or exam or anything like that. Just trying to be complete with what I'm telling you. So we've got this confidence interval equation. We're also going to refer to this as our margin of error still. So whatever we add and subtract to our sample statistic, we're going to call that our margin of error. Right? It's actually appropriate to deal with a proportion. You're not really supposed to deal with a sample mean, but it's way easier to talk about it. It's always going to call it the same thing. But here now we're actually being not the math people in the math department wouldn't be mad at. So let's try to work through an example. Right? So if I'm looking at, gave out this survey, and this is kind of, I guess, a little outdated as an example now, but it was an actual survey that I saw in some news report or some media thing from Indiana. So before the Affordable Care Act was kind of passed, they sent out this survey and said, do you think that insurance companies should cover pre-existing conditions? Right? They had 81 people that they gave this survey to, and they found that 63 out of the 81 said they were in favor of it. Right? So based off this sample, they wanted to build a confidence interval for the true population portion of residents. I think this was actually Indiana residents. I didn't say that here, but it was Indiana residents. We're actually in support of healthcare coverage covering pre-existing conditions. So it's a little bit tricky here, but what would our sample proportion be? Right? Yeah. Yeah, so it's 63 over 81, right? It's the number of people who responded that they were in favor divided by the total number of people asked. So this is what, 7/9. Our sample size, we asked 81 people. And the last thing we need is, what's our alpha here? The 99% confidence level, alpha would just be percent outside the interval is 1%, in decimal form, 0.01. Now, when we're thinking about this sample proportion, it should always be between what two values? Let's say nobody was in favor of this. What would our sample proportion be? 0 over 81, so 0. What if everybody was in favor? 1, right? So proportions kind of follow like similar rules of like probability. Like it has to be somewhere between 0 and 1. Right? And I think when we look at some data in Excel, this will make a little bit more sense as well. So from here, I mean, we should start plugging things into that equation for our confidence interval. So our sample proportion is 7/9. We'll add our margin of error at the upper bound, subtract the margin of error at the lower bound. Now, we have to look up this z-score that gives us 0.01 over 2 on each side. I'll show you how we do that in a second. And then multiply that by the square root of that sample proportion times 1 minus that sample proportion divided by our sample size. Okay. So 0.01 divided by 2 here is 0.005. So what I'll do is I'll go to my table. I know the area that I want in the tail is 0.005. So I'm going to look at these values in the middle because those reflect the probabilities or the areas in the tail. So it looks like 0.005 is in between these two values. So -2.57 and -2.58. We'll use kind of the higher of the two. We also know that the signs are built into our lower and upper bound equations. So I can just use the absolute value, or that just 2.58. Okay. And then from here, it's just a matter of getting this entered into our calculator, right? Any questions kind of over that process at all? Okay, so kind of have all that outlined here. I would probably suggest, makes it a little bit easier, especially when we're doing this on a calculator, to calculate that standard deviation of sample proportions ahead of time. That way you're just plugging in one value, right? Just makes it a little bit easier. You don't have to do that. You can do it all at once if you're comfortable. But what we end up getting is a confidence interval that with 99% confidence, I could say that the true population proportion of people who are in support of covering pre-existing conditions is somewhere between what, about 66% and 90%. So if I'm a politician thinking about, we're about to push this act through, I should think like, yeah, worst case scenario, the true population proportion of people who are in favor of this is like 2/3 of the country, right? So we should, using this confidence interval, I should be pretty confident in pushing this act through that most people are going to be in support of. Questions there? Yeah.
So to do the equation over there, we have to use we always have to use the standard deviation equation first.
You don't have to do it. It just makes it a little bit easier when you're adding this in your calculator because, really the order of operations, depending on how you're doing this in your calculator, you might need to put some parentheses in here. And so I just always suggest, like, if you're having difficulties doing it all on one line, try to break it down into parts, right? Yeah, that's the only reason why I'm kind of showing. Questions? So the slide that I kind of really went through quickly is this guy. The reason why I threw this in there is I wanted to point out that we're going to start seeing the same Z values show up all the time when we're building confidence intervals. Because we're always looking at kind of the same benchmark, 90, 95, 99% levels. So the alphas are always going to be the same. So when I go to look up the alpha over 2 value, it's always going to be the same corresponding Z score. So I'll start seeing these values pop up a lot because they kind of correspond to some of these more popular benchmark values. Okay. So we get to this one. We got one more. So I'm going to see if you guys can kind of do this one on your own here. And then we'll come together and talk about it. So let's say, and this is kind of using 2016 data, but there was a poll given out where 912 people who were registered voters responded, and they found that 46% of people said they were going to vote for Clinton. I wanted to, in the 2016 election, so if I wanted to derive a 90% confidence interval for the true proportion of people who would end up voting for Clinton, like this was prior to the election, what would that be? So I've got a sample proportion here. It's told me a little bit differently, but 46% would be a sample proportion of 0.46. Right? I've got my sample size pretty large here, so I should be able to get a pretty narrow range of values. And then I want the 95% confidence interval, so I can figure out what alpha should be based off of that. I can then look up the Z value that corresponds to seeing alpha over 2 on each side of my interval. And I'll give you guys a couple minutes to work on that. So if you want to talk to people around you, work with people around you, you might understand part of it that you don't, and vice versa. So yeah, give me about 2-3 minutes, and we'll kind of come together and talk about how we would work through this one. Also, you'll notice none of these upper and lower bounds are the same. So really, once you find one of them, you should be able to identify what the correct answer is. All right, I see a lot of people working. So try to work this together. So I'm going to use this equation right here. What's my sample portion? So that was 0.46. So just plug in that everywhere where we see it. My sample size is what? So if I did calculate the intermediate step here, did anyone do that? I'll try to do it once. What would you find for the intermediate value? 0.0165. 0.0165. Sounds right. So really the only other thing I need here is that Z value. Okay? What's my alpha for the 90% confidence? Yeah, so I need to find the Z-score that gives me 0.05. If I look that up, what's that correspond to? So I'm in between 1.64 and 1.65. So I use the higher of the two. From here, I've got everything I need, right? Plug in here. I add that margin of error to my upper bound. I subtract it to get my lower bound. I'm not going to give you the answer here, but you've got everything you need. It should be relatively easy here if you've got your calculator. So paying attention, following along. Give you another 30 seconds here. You should be able to kind of figure out what the correct answer is. All right, still open. So. We haven't difficulty kind of lining that up. So if you haven't gotten an answer in, kind of take your best guess here. We'll close it out. And we'll kind of talk about, work through it. Okay. 19 of us. Didn't think it was that smart. We got 20. Everyone's got their answer in. Okay. We'll close it out. So 21. So, right, we found that Z value of 1.65 already. Oh, not 1.65. Yeah, that was what it was. My bad, 1.65. We identified kind of what that intermediate value was if we wanted to break it down that way. Now it's just a matter of getting this enter into our equation or calculator, add to get our upper bound, subtract to get our lower bound. We should get what? 0.4382 and 0.487. Any questions there? Saw some puzzled looks. Yeah.
I've been getting like different.
Here. All right, so if we do what? 0.46 plus 1.65 times 0.0165, I think it was. So I guess we're rounding it to the second decimal, 0.4872. All right. So 0.4872, but we have to round. I mean, it's got more decimals here. I'm using Excel, but I should be getting that. So one thing that sometimes, I don't know what calculator you're using. Sometimes I tell people it's actually easier to do confidence intervals backwards because the order of operations will never be wrong if you work this way, right? If I take 0.0165, multiply by 1.65, hit enter, and then add 0.46 to it, I can't screw up my order of operations. If I somehow take 0.46, add 1.65, and I hit enter, and then multiply it by, well, now I've actually multiplied this entire thing by 0.0165. So sometimes with these confidence intervals, working backwards actually prevents some word of operation mistakes. Any other questions before we keep moving here? So I think, well, I've got Excel open here. I'm going to take, well, actually, no, I want to finish that example. I think I know what I have in here. So I won't ask you guys to do this one, but I think it is interesting if we kind of talk about this. So the same poll found 40% of people were planning to vote for Trump in the 2016 election. We walked through the same kind of steps. Standard deviation is a little bit different here because we've got a different sample proportion. I plug everything in and I end up with this confidence. So the reason why this is kind of an interesting example is, no, I already forgot those values. Just keep that on. So if I'm thinking about what these confidence intervals are telling me, they're telling me the proportion, the true population proportion of people who are going to vote for these different candidates. So now I'm looking at Trump here, 0.3732, 0.4267. I have a blue one, but I guess I could make this real political. That being Republican here. So we go back to Clinton. Right? So this kind of represented the true population of people who were going to vote for Trump was somewhere in this range, based off of my sample. The true proportion of people going to vote for Clinton was 0.4328 and 0.4872. So if I'm looking at this with 90% confidence, I can say the true proportion of people who are going to vote for Trump is somewhere in this range, and the true proportion of people voting for Clinton is somewhere in this range. Well, those don't overlap. So even worst case scenario, if the true population proportion for Trump was here, and a true population proportion for people who voted for Clinton was here, with 90% confidence, I can say that, or I could have projected that Clinton was going to receive a higher proportion of the vote than Trump, based off of my sample. Now, kind of already mentioned, I think we were talking about biases, why maybe some of this survey data was a little bit biased or skewed, but right, my confidence intervals don't overlap. With whatever level of confidence it is, I can say that this person is going to receive a higher proportion of the votes. This is basically how they make projections for elections, right? I don't know if anyone is interested in politics at all, but whenever you look at kind of these projections, they always tell you the current polling is 46% with a margin of error or plus minus 6%. That plus minus margin of error, that's what we're finding, right? So all those like polling data you saw before the elections, they were basically just creating confidence intervals. Now they weren't giving it to you as a lower upper bound, right? Because if they give it to you as a lower upper bound, it kind of like rely, you know, if I'm the media, I can tell you that, the proportion of people who in this survey for Trump was what, 0.4 and Clinton was 0.46. So their confidence intervals will be centered around that. And for the media, they're like, oh, well, I can make a projection here, right? The sample proportion was way higher for Clinton. But if you take that margin of error and actually calculate what the upper and lower bounds are, potentially, in this case, that isn't the scenario, but potentially, at some point they overlap. And if they overlap, then I can't really say who's going to get a higher portion. Because the true portion for Trump could be here, true portion for Clinton could be here, in which case that would be a projection that Trump, that potentially Trump could win. Or the true proportion of people that were going to vote for Trump is here, true proportion for Clinton's there, in which case it would be the reverse outcome, right? So anytime these confidence intervals overlap, we can't really say anything with whatever level of confidence we build those confidence intervals with. Right? Yeah.
When you say a margin of error of, let's say, 6%, are we talking the size of the actual interval, 6%, or are we talking from, let's say, the middle to an end, 6%, where it would be a span of 4%?
Yeah. So it'd be, the span would be twice, right? Because this reflected our margin of error. So a margin of error of 6% means we were adding and subtracting 6% to either side. Yep. So, kind of interesting. I mean, it's a little bit, we're over the election now, so that's good. But right, for the next one, right, we can do something like this and make projections for what's going to happen. Now, the actual scenario is like this. So maybe I'm a news source and I want to be able to project the election. I build these confidence intervals, like I say, awesome. With 90% confidence, I can tell the public Clinton's going to get a higher proportion of votes than Trump. What happens if I want to say it with 99% confidence? Why do you think that this media source probably didn't choose the 99% confidence level? If I want to say something with a higher level of confidence, what happens to alpha? It gets smaller. So if I have a smaller area in the tail, what's going to happen to my z-value? S gets larger. So if the z-value gets larger, I'm adding and subtracting a larger amount to that sample proportion. So my intervals get wider, and they're already pretty close. My guess is if we actually calculate this out at 99% level, then they overlap. And now I can't say anything with 99% confidence. Right? So always think about why they're choosing to stop the confidence level, whatever they did. But yeah, pretty relevant, I guess. An interesting example of kind of use these proportions for. I think I went through, get you out here a little bit. I got to show you something else in Excel, but we won't spend too much time on this. It's really interesting how to look at these slides and how just different numbers, really. It's the same sort of idea. In the last election, they actually, so that I remember I grabbed, that was actual data. I'm not making this up. So that was actual data from, I believe, I grabbed it from Fox News because I thought it would be the most biased in terms of projecting that Trump might win, and it still got the projection wrong. And then in the next election, 2020, a lot of these polling places realized like we're doing something wrong because we all made the wrong projection last time. So they got a little bit better. The data was a little more reliable. In fact, the only one that got the 2016, or the only major one that got the 2016 election right, I think it was like, I forget the name now. I think it was like Reuters, but I might be confusing that with something else. And so whatever that source was that got it right in the first election, he grabbed data for the 2020 election prior to it, try to, in classes I had at the time, we try to project what it was going to happen. So there's this survey by that company, and they found 54% of people who vote for Biden. You could build a 90% confidence interval here, right, for him. And then Trump's was significantly lower for the 2020 election. And notice here, I mean, we're far away from any overlap. So I felt pretty safe in the projection for that election, at least in terms of the popular vote, right? The electoral vote, that'd be a whole different nightmare we have to deal with. We have to do it state by state. We build these confidence intervals, and no one wants to do that. But for the popular vote, we could make these projections just by simply kind of constructing these confidence intervals. So that was that. I then used like a different one that I thought would be more biased the other way. No matter what I used, like I could barely find. There was really none that kind of had this one. I think just slightly had an overlap, but we saw what the outcome was anyway. So you could do any, maybe the upcoming midterm election. If you're interested in a candidate, and you could go out and find some survey data. Which, in looking for this, I found that there's tons of websites that have like surveys over. I mean, local politics is everything, right? So kind of interesting. So with this idea of proportions and building confidence intervals, we saw how we could do sample means in Excel. We can also do sample proportions. Right? So over here, right, I'm going to do a similar setup. I'm going to calculate the intermediate value as well, just to prevent myself from making some order of operations or parentheses mistakes. So here I'm going to find the same standard deviation of my sample proportions, right? It was kind of represented by this. I can find my sample proportion or my mean proportion here. I think I'll call it sample just to kind of line up with the way that I usually say it. Now, to find a proportion from data, I had this example originally, which was I wanted to say what proportion of schools have more than 10,000 students. I've got a, I think, more interesting example that we're going to actually do. So I'm going to delete this column. If you want to follow along, just type in exactly what I have. So here I'm going to do, does the school have more female undergraduates than male? Okay. So I just deleted that column of data, highlighted it, hit delete. I'm then going to use this if statement. Now, I wouldn't expect you to do this on like a homework or anything, but it's a way that you can construct kind of one of these 1-0 variables kind of easily. Now I'm just going to say, okay, if female undergraduate enrollment is greater than male undergraduate enrollment, that's what I want to check to see if that's true. If it's true, comma, put a 1. If it's false, comma, put a 0. Okay? So I can enter this in for the very first observation. And then if I get this to be this bolded black plus sign and I double left click, it'll fill this in for every observation I have here in my data set, right? So every time I see a 1, that means female undergraduate was greater than male undergraduate enrollment at that university. Every time there's a 0, it means they had more male undergraduates than female, okay? So you can kind of notice Ball State's pretty skewed towards female, at least in 2012 it was. Okay. So I've got all these 1s and 0s. If I simply take the average or calculate the mean for a binary variable, what that's really doing is it's adding up every single observation. So it's adding up 1 plus 1 plus 1 plus 1 plus 1 plus 0 plus 1 plus 0. Well, every time there's a 0, it doesn't influence my numerator at all. And then once it adds all those up, it divides by the sample size. I think I erased already, but that's really counting up the number of schools that have more females than males, and then dividing it by the total number of schools in the data set. That's just my sample proportion. So in practice, when I have a 1-0 variable in my data set, if I find the mean of it, really what I'm doing is just finding my sample proportion. Okay. So anytime I have a 1-0 variable, finding the mean of it, I'm really just calculating a sample proportion. And then sample size, we can still use that count function. Go over here, select that variable. Now I've got everything I need. I've got my sample proportion, I've got my sample size. The only other thing I need to do is look for that z value that gives me alpha over 2 on either side of my interval. Okay. Well, that's going to look no different than what we were doing over here, right? So norm.s.inv, I want alpha over 2 on each side of my interval. I have to remember, oh yeah, this is going to give me the negative value. So I need to take the absolute value. Oops, that's not what I want to do. There we go. Put my other parenthesis. Should get the exact same value as before because I'm looking up the same alpha over 2, right? I'm using those same kind of benchmark values. Copy that down. Now I get my z values. From here, I can calculate that intermediate step, which is the standard deviation of my sample proportions. That's just going to be the square root of my sample proportion. I'll move this out of the way so you can see it. Times 1 minus my sample proportion divided by my sample size. Once I have this, I've got the 3 components that I need to find my upper and lower bound. So, so equals, take my sample proportion, subtract that z value times the standard deviation of my sample proportions to get my lower bound. If I want to copy this down, I said, oh yeah, I've got to freeze everything except for my z value. All right, when I'm building different levels of confidence intervals, the only thing that changes is my alpha, or that is z value. Okay. So once I have this, I can copy that down to get my lower bound. Now I could retype that same thing in for my upper bound, or I could use that, what I think is a shortcut, which is double click on the cell to see the formula, copy it, hit enter to get out of the cell, paste it over here. And now the only thing that we have to change for the upper bound is we're adding that margin of error instead of subtracting it. Okay. Now I copy this down and I've got my 3 confidence level or intervals built relatively quickly. Okay? So real similar process to what we're doing with the sample mean. It's just that, right, the equation that we had changed a little bit because that standard deviation of our sample proportions was a little bit different than that standard deviation of our sample means. Okay. So I went through that kind of quick. Do you want to see any of those cells again, or kind of a question or anything there? So I mean, mainly what this exploits is the use of that norm.s.inv function to kind of look those values up in the table for us. Other than that, I mean, one new thing that we're kind of looking at is if we just use the mean or the average function for a 1-0 variable, that gives us our sample proportion. And then from there, it's kind of just using Excel to be a calculator, right? So we don't have to round things. We can be very exact, right? And we can get this out to whatever decimal level we want. So this should be everything you need to kind of do those last 2 problems in the Excel homework. The first problem comes from like the old stuff where we're only looking at samples. We're just looking at an original normally distributed variable. Okay. Questions on this? Now's the time to ask. Okay with this? So I've got one other thing I'm going to show you. I put another file up there called CI grade data. Okay. So, you know, maybe you don't believe necessarily what I'm saying, that, you know, the whole idea of these confidence intervals is that when I take one sample, that I can be guaranteed that 95, so if I want to do 95% confidence level, 95% of the time, if I just take one sample and build a confidence interval around it, it will include the true population mean. Now, what I'm going to do here is kind of cheap. Okay. So I've got population data here. And this was like every student, I think, that has taken, well, it's pretty up to date. Almost every student has taken a stats class from me, and what their grade was to the nearest integer, right? Just to make the numbers a little bit easier to look at. So I can calculate the true population mean. I can calculate the true population variance, and I have my population size, right? What I then did was kind of use this thing in Excel, which is a random number generator. So I'm generating a random number from 2 all the way down to whatever the, what is it? E2 or, oh yeah, right here, to the very last kind of person in my data set, right? So I'm going to generate these random numbers so that I'm randomly selecting a student ID here. And the idea was just kind of assigning them 1 through 431 or whatever. So I'm going to have a bunch of different samples. So here I kind of have the first 3 labeled. You can kind of see out here. Here's all my other samples as well, right? So I generated all these random numbers. Oh, here, I'll show you these ones, right? For 1,000 different samples. So I've got 1,000 samples. They're all of size 50. So notice I generated 50 random numbers for 1,000 different samples. For each one of those samples, I then calculated my sample mean, right? So I've got 1,000 different sample means. I'm then going to construct confidence intervals around those sample means. I think what I chose here was, we'll start out, we'll do a 99% confidence level, okay? So I set alpha to be 0.01. So down here, I had an equation. Now, I didn't break it down into parts, right? Notice I kind of even found the z values all in the same cell. So when I broke it down before in those examples, I could do it all in one cell. If I don't want to see what those z values are or the standard deviation of my sample means, I can type this all in at one time, right? Now, I can kind of have an example here where I knew the true population variance because I had the population data. So even though I'm basing this confidence interval off this first sample, I can use that true population variance because I also have the population data. So I build my lower bound, and same thing, but I add to get my upper bound. I then kind of did something I wouldn't expect you guys to do, but I played around with some if statements. So basically what I'm doing here is I want to put a 1 if the true population mean that I have up here is above the lower bound or below the upper bound. Said differently, I'm just putting a 1 there if it's in my confidence interval, and let's see if there's any zeros here that are nearby. Maybe these all, come on. Let me see if I can get, so every time I click on these, they'll generate new random numbers. Well, I'll change alpha so I can show you. We'll change alpha to 0.1, right? Should get a lot more. There we go, right? So notice for this confidence interval, population mean just fell outside of it. For all these other ones, that population mean was somewhere within that range. Okay? Well, then what I did is said, okay, I'm just going to add up the number of times my population mean was in my confidence interval across those 1,000 different samples. So I added all those ones up, and then I have the number of samples here, which is 1,000. So then to find the percent of my confidence intervals that included the true population mean, I just took the number that included it, divided by the total number of samples, 1,000. And notice when I set alpha to be 0.1, for these 1,000 different confidence intervals, 90.7 of them included the true mean, which lines up with, that's why I'm saying it with 90% confidence. Now, it's not exactly 90 because I only took 1,000 samples, right? To get it to be even more precise, I should probably have like 10,000, or theoretically, I really need an infinite, which isn't practical, right? But I'm just trying to use data to kind of prove this to myself as opposed to just the mathematical proof. And notice every time I click on these cells here, it generates new random numbers. And that percent is always floating right around 90%. And I could also kind of change alpha to be 0.1 or 0.01, sorry. And then I'll kind of notice it's floating right around 99%. A little bit lower, sometimes right on, right? Just kind of depends on the random numbers that were generated. So I don't know, I always thought this is kind of a nice kind of example to really prove to ourselves using data that our confidence intervals really will include that true population mean, whatever percent of the time that kind of matches up with our specific alpha, our specified alpha. Okay. Any questions over anything else before I kind of let you guys get out of here? This is definitely something that more than I expect you guys to do, but I always think, for some people, this really helps kind of be able to visualize what we're doing. Okay. So if you need any help kind of finishing that Excel assignment the rest of the week, and my office hour times don't work for you, feel free to email me or reach out. We can set up another time. I want everyone to get as many points as possible. I'm starting to get concerned with the number of people that are showing up to class. So as long as you're kind of showing up, good for you. Probably have an easier time. So maybe I'm speaking to a brick wall here. But I'll see you guys on Wednesday. Try to stay dry out there. And good luck kind of finishing up this homework.